University Franche-Comté and CNRS, and he's going to speak about towards a Wong-Zakai approximation for big order generators.
So I thank the organizer to have given me the opportunity to give a talk. So this beautiful activity. So this talk enters in the beautiful probabilistic index theory of Bismuth. Namely, Bismuth in his index theory, he considers power of integral, that is probability, and after it is by probability you see the formula which are simpler to check by analysis. And this talk corresponds to a question of analysis, Paropoulos and plenty of people which are not satisfied that probabilistic method were working only for non-Markovian for Markovian semigroup, but with semigroup with present positivity. So for instance, Bismuth proof of an index theorem gives Berlin-Verrin proof of an index theorem. And Getzler, he has a short proof of an index theorem in 5 pages, which is, and they are marvelous normalization, marvelous scaling. Never explained Getzler when he has got this marvelous scaling. And by my paper about Dirac operator, you have a paper, you see this marvelous scaling. It was published in Compte Rendu in 1986. And so, okay, and index theory requires Dirac operator. So let me introduce the subject. You consider L with some vector fields. You consider some vector fields. Here they are considered as a one-order differential operator. You consider this generator. You consider the equation, it is plus here. And so, you have PT of x equal expectation of fxtx. So according to the general theory of Hunt, there is a stochastic process if and only if the generator satisfies maximum principle. And here you have more than a stochastic process. You have a stochastic differential equation in certain conditions. Because the M for F, you consider M vector field, you consider M flat Brownian motion on RD. You consider the stochastic differential equation starting from X. And you have this formula. So now what is Wong-Zakai approximation? It's a generalized stochastic differential equation. What is Wong-Zakai approximation? You consider the polygonal approximation of a Brownian motion, and you consider an ordinary random differential equation starting from X. And the theorem of Wong-Zakai said to you, if you consider the f of xtmx, it tends to f expression of xtx, and it is better, it works for the whole process, for all the trajectory, all the time I will say, there is no whole trajectory, it works only for a certain group of things I will say. So now you consider xi, you have a divergence on a compact manifold, and you consider Lk equal minus k sigma xi to k. So it is a big power of k. So it does not satisfy maximum principle. You have in my theory, I studied since 7 years about the stochastic analysis for for 8 years for non-Markovian semigroup. You use only basic theory of elliptic theory. So, and you suppose we span all the space, and by we generate self-adjoint extension, essentially self-adjoint extension, and by abstract theory, you have a semigroup associated to that, which is generated by the with operator. So what will play the role of flat Brownian motion? Because it's the LFK. You consider the generator minus k sigma 2k 2w 2k on Rm. So it is a flat generator It is a flat generator, and it will satisfy the role of Brownian motion in this theory. And by elliptic theory, the semigroup it generates a semigroup PTFK flat, and it is an kernel by abstract theory or elliptic operator. And recently, I showed for compact manifold by using Mann-Lemma integration by part for any pseudo-differential operator positive symmetric. I show the existence of density, but I didn't show from in the non-compact case. It is a hit kernel. Yeah. It is a hit kernel. Okay. And formally, if you suppose you have a formal pathwise measure, PTFK equal, I will say to where comes this formula later. QFK, a formal pathwise measure, such that formally, some of formal path space, we have formally a process, but here, the hit kernel chain of signs, it is a big difference. Here, all chain of signs, it is a big difference with Brownian motion and probability. So it is represented by this full path measure. If you were able to solve a formal Stratovich equation, okay, your formal path measure, flat path measure, your formal Stratovich equation, and formally you should get that formula. Okay. So now you associate the Wong-Zakai operator. You consider your ordinary differential equation, but instead of taking the DWTN with Gaussian law, you take the flat higher order hit kernel. And so now, and you introduce the Wong-Zakai operator, some QTFX, and I sum to n FXTWX, PTFKW, And now you work on an operator of length 2K. So you know the time square for Brownian motion is square root of t. Here you consider an operator of length 2K. So the time square operator in 1 to 2K, P1 FKW, where you use this ordinary differential equation. Where is the problem? Here it's not positive. It is not positive. It's change of signs. The problem is change of signs. Okay. So now, the first theorem of Wong-Zakai, you suppose that the vector field excite commute, and you suppose it compact, you are in an elliptic situation, all is divergence free, and so on. So the Wong-Zakai equation, you consider the Wong-Zakai kernel at the power n convolutional to x to P1 of the curve if f is in L2 of x. So if you put t over n, it tends to PTKAN. Okay, but you see, it works only for the semigroup because you enough the full path measure. It's something else. Suppose in compact, it is a compact Lie group. You suppose the extremes are element. Here, vector fields are not defined as a one-order differential operator, but are defined as element which depend from X. So you consider compact Lie group G. You consider Xi element of a Lie algebra constituted as right invariant vector fields. You are a Lie group, you have a right action. Element of a Lie algebra can be considered as vector fields as element of a Dodger space on the starting point. We consider the right invariant vector field. We consider the right invariant differential operator. Here we are considering the invariant operator. You consider, you suppose you're an elliptic situation. And you suppose ellipticity. And you are in compact case. You have an elliptic operator on compact case. It has a discrete spectrum, lambda larger or equal to 0, associated to eigenvector, all discrete. So, the second theorem of Wong-Zakai, if f equals sigma a lambda f lambda, you have a very strong hypothesis here, such that C over square lambda is smaller than infinite for all C positive. Then the Wong-Zakai approximation f converges to in L2 gamma to P1 of K. As a matter of fact, with Wong-Zakai application, you consider polygonal approximation of differential equation, and so. So I will give a proof later, but oui.
Usually in Wong-Zakai, when you consider polygonal approximation, you get the limit is another equation.
It is yes. It is a certain. It is an operator written in Hermann's form. All the operators I consider written in Hermann's forms. Yes, but in my theory, for a moment, I can give generalization of my integration by part in my calculus, standard deviation, rules of dependent parameter, but things. But to understand stochastic differential equation, for a moment, that's an open problem. But here, I will explain later. I will explain now these things. So, what is the difference with this Wong-Zakai approximation and Stratonovich and traditional approximation? We work on RD. You consider the generator sigma alpha x d alpha dx alpha. We suppose it is symmetric. According to the general theory of elliptic equation, you are introducing this symbol, and you suppose the symbol is larger. It is of degree p, and 6ip minus c. So it is ellipticity. Yeah? You suppose it's positive symmetric, and you consider toujours operator for semigroup which are associated. Semigroup which are associated. Okay? Starting from F. Now, the classical method of approximating the so this is written in iter forms. The operator are written in iter forms. In the operator I have written, I had spoken before, the operator are written at the Hermann's forms. Here they are written of iter forms. So now, what is the parametric method? You consider the family of operator. You froze the time x, the starting point x. You froze. And you consider the family of semigroup starting from x. Here, you have frozen operator. It is P0 x fy equal y. Okay? And you will see, I will explain, it corresponds to the Euler-Maruyama scheme. And so you consider the kernel f done pt qt pt f of x equal pt of f x. That means you consider the froze generator, the froze semigroup with the same starting point. A parametric method say to you Q1 over n P n to F to P1 FF. The standard method of analysis. So What is the relation with parametric method? First of all, parametric method, because I was motivated, you are motivated by an interpretation of path integral. You consider here it is you consider the Fourier transform of LF of F is given by this formula. So the Fourier transform of its semigroup is given by this formula when you take X. And by inverting Fourier transform, cutting the time in small pieces, you arrive to traditional Hamiltonian path integral or integrate path in a moment of space. The full theory, which is not rigorously defined, which is, I think, originally due to Clauder, to try to explain for any elliptic operator the each semigroup as a path integral. For diffusion case, so now you consider you consider the operator if degree 2, and you have these things. And you have an Ito equation associated to it. And to the Ito equation is associated the Euler-Maruyama approximation by electronic subdivision. And the Euler-Maruyama approximation give you the parametric method of Euler-Maruyama coincide in this case. But in some case, the parametric method works for a semigroup only. The Euler-Maruyama works for the whole process. So now you introduce a non-standard approximation of a semigroup. So I will give a proof now. Proof of theorem 1. You have a compact case, you have a compact case, you consider the eigenvector associated to eigenvalues of your operator. And to an eigenvector of lambda, you apply formally this series, because formally the dynamic is give you the exponential of your vector fields, deriving of vector fields. And you have that formally, this series like this. Now, it is formal series. But in fact, it will be a true series. Namely, you work on a flux, all the vector fields commute, for instance. So here, you recognize, and now, what is the main remark? The main remark, if you consider the flat internal, if the flat internal, the flat semigroup is formally the exponential of your generator. And here, the generator does not depend on X. So you apply this to polynomials to the generator, and you find some theorem Wn1, L1, Wn, LMP1, K, W equals 0. If one over I is not a multiple of 2K, and this type of things. So you apply formally. But depends you put minus in the generator in front. But you apply formally this series in order to get these things. Now, when you work inside, you recognize for an eigenvector Q1 FK, all is commuting. You recognize the generator at big power. Because we integrate, and you recognize Q1 over K F lambda, L exponent minus L lambda F lambda, where it is, and so in such a case, the Wong-Zakai approximation is exact, is rapproched to the Doss-Sussman expansion of Stratonovich equation. Stratonovich equation when vector field commute. In such a case, the Wong-Zakai approximation is exact. All is exact. Okay. Proof of theorem 2. So now, for proof theorem 2, these are not commute. I should recognize, not recognize your generator in big power. But for a first term, so for a term n prime which are smaller than 2k, it is equal to 0 by that. And for n prime equal to n prime equal k, you recognize the generator. And for every term, you have an error term to estimate. An error term to estimate. Because it is morally 1 plus minus LT, F lambda, morally, plus error. Or the error, you do very rough estimate for the error. You do very rough estimate for error. And so, for very rough estimate, you arrive these things. You can estimate by using Golding inequality. Now, what is Golding inequality? You say you can estimate if you it is a vector. You can if you apply xi to f lambda. Yes. You have another problem. You estimate the error term. You use, if you consider the eigenspace associated to the eigenvalue lambda, you define a representation of G because you are on a Lie group, but it does not act diagonally. Yeah? It is a representation. Huh? It is like this. For generally, it is not for Laplacian on G, and so the vector field acts on E lambda. And you, to conclude, you estimate, so to estimate the error term on each eigenvector space, you apply Golding inequality, which gives you this language. And so this can be estimated in terms of lambda. So I give you some references. So for the exact representation of the paper of Doss and Sussman, in the case of diffusion, I'm interpreting semi-group with the theory, my proof with Benarous, a positivity theorem of the heat kernel where Bismuthian collision plays a big role. And so, I have introduced the Wong-Zakai kernel for diffusion. And here the error term can be estimated much more simply. And so you have no problem. So now I have done a review of this stochastic analysis for non-Markovian semi-group in Russian Journal of Mathematics. And these things in 7 years are published. I have done a review. I distributed to several people here. Analysis of pseudo-differential operator. I've done several talks about this subject in analysis included in France. And for Wong-Zakai approximation, you can look at the book of Professor Ikeda, the second edition. He mentioned my paper. They mentioned my paper. So, and for basic tools of elliptic theory in compact case, you have a book of Gilke. So I study elliptic theory, basic tools of index theory. And so, for instance, in this book, if you consider pseudo-differential positive pseudo-differential operator on a manifold, it has a neat kernel, a semi-group has a neat kernel. And here I can show that in 1 page by using tools of Minimal calculus. So I thank you all for your attention.
So, any questions? This one.
Are you aware on framework of starting number finally dimensional plan? It is somewhat manifold.
Yes.
So suppose can you do it in intermediate for FD2?
I don't know. For what it's only the beginning. It's only the beginning. So I don't know. Yes. For instance, and now a big question is the following, because in a lot of generator, and what are the generator who can be formally, whose the semigroup can be formally represented by the stochastic differential equation in this sense. And here, in order to state this hypolepticity problem for elliptic differential operator, it is I use following the request of Bismuth, large deviation Malima calculus, because Bismuth is a large deviation Malima calculus. He did an intrinsic variation of operator of Laplace spectrum of Brownian motion of manifold. So here I use an intrinsic variation of a generator by using fractional power in Seeley type of a generator. Okay, so because you have Gersdorff formula, you know Gersdorff formula for stochastic process. You consider a very rough process. You perturb it by a nicer process, but two processes are related. So you have a very rough term in elliptic theory, is the term of a big order. You perturb it by a low order, and you have a Gersdorff formula, this type of things.
This one.
In classical approach to Wong-Zakai approximation, you get a result of rate of convergence of solutions. You can prove pathway convergence. Could you do it the same in your framework?
Oh no, because I use basically the full global property of a generator.
Okay.
Yes, in this, I use pointwise estimate. You have pointwise estimate this, but here you use global property. I don't say it is satisfactory, but it is the beginning of these things I do since 8 years. Of beginning, I saw that in my title told, but here for positivity, you have a full, you have no problem. You see, I use the spectrum, I use probability of a spectrum, I use probability of these type of things.
Okay, let's thank the speaker again.
I remove the key.